Welcome physics students. We are doing the answer key for the Unit 5 review worksheet. This section right here on an energy summary is something that you can just look at in the answer key. There's not much more explaining that needs to be done than what you'll find there. So go ahead and look up the answer key document and check your answers for the first table. But what I will do is walk you through some of these calculations down here at the bottom. So what I always encourage my students to do is to underline the important information, or in this case, we will highlight it. And I've got a 1.5 kilogram kitten, and it's jumping down from a 2.0 meter high fence, and we are trying to find its GPE, which we know to be gravitational potential energy. So I'm going to write down my knowns, or my givens. I have a mass of 1.5, and I have a height of 2.0, and my unknown is my GPE, has the equation mass times gravity, MGH, mass times gravity times height. So I'm going to go ahead and plug in my values here. I've got a mass of 1.5 kilograms. I've got a height of 2.0 meters. And of course a gravity of 9.8. It's in a different order, but it all comes out to the same thing. Meters per second squared is the unit for that one. And you end up getting a gravitational potential energy of 29.4 joules. Now, if you wanted to, you could write it out as kilograms times meters squared over seconds squared. That's just fine. But in general, you do want to know what the unit for any type of energy is, and it's J for joules. What will be the kitten's speed? Now, when it's asking you for speed, and of course we are in an energy unit, you know that speed is related to kinetic energy. So this is my KE. Well, based on conservation of energy, we also know that the gravitational potential energy converts or transfers to fully kinetic energy right when it is approaching the ground, or close to the ground but not quite stopped yet. So whatever this value is here, the 29.4, that's going to be our kinetic energy due to conservation of energy. And we know kinetic energy has the equation 1/2 mass times velocity squared. So if we plug in our mass of 1.5 that we got from the problem, we should be able to solve for velocity. So here I have, I'm just going to work this over, 29.4 joules is equal to half of, this is 1.5, 0.75 to be exact, 0.75 times velocity squared. So if I divide the 29.4 by the 0.75, 39.2 is our V squared. In order to get rid of the squared, we take the square root of both sides. So in the end, we end up with a velocity of 6.3 meters per second. The next question we have is a car traveling at a constant speed. So the mass is 1,000 kilograms. It has a speed of 30 meters per second, and we are trying to figure out the energy. Obviously, how much energy is transferred as the car comes to rest. It's going to start off as all kinetic energy because there's motion, and when it comes to rest, obviously we're going to transfer that kinetic energy into something else. And when we're thinking about how a car comes to rest or how it stops, you use your brake, and the brake is creating friction, which is thermal energy. So all we need to do here is calculate the kinetic energy, because we've got a mass of 1,000. We've got a speed of 30. And this is related to kinetic energy, 1/2 mass times velocity squared. So then 1/2 1,000 times 30 meters per second squared gives us 450,000 joules. And all of that energy is going to transfer into thermal energy once it's stopped. Now, if the car stops in 100 meters, what is the average force applied to the car? So here we've got a force, and we don't have a spring because we would only see force in two equations, which would be the force of a spring or the work equation, work and power equation. So here we've got a distance of 100 meters. We've got a force applied to the car. That's our unknown. And since we know that the force was a frictional force that caused it to stop, this is going to be our energy, which is basically work done by friction. So our work value is 450,000. That's equal to force times distance. Our distance here is, let's just plug it in now, 100 meters. And all we have to do is divide 100 meters to both sides. So, in the end, our force, which is in newtons, is going to be 4,500 newtons. Okay, the next question is about hulky and bulky. So we've got a bunch of information here. We've got hulky and bulky, so both of them are 60 kilograms. For hulky, he reaches a height of 3 meters. We can call that our distance. And does it in a time of 2.2 seconds. For bulky, we've got a height of 2.5 meters and a time of 1.8 seconds. So this is for bulky, this is for hulky. Okay, before we do this, let's talk about what we're solving for. It says, what is each athlete's power? Well, the equation for power is work over time. And work is equal to force times distance over time. Another way to do this, and you can also think about it in terms of energy. Force, in this scenario, is the weight of hulky and bulky. It's mg. The distance that is traveled is a height. We have height above the bleachers. So if you write out the equation for force and turn distance into height, because the height is the distance, you actually get the gravitational potential energy equation over time. Now, work is energy. It's energy transferred in, and as hulky and bulky are doing work to move up the ramp, they are gaining gravitational potential energy. And so this is the gravitational potential energy gravitational potential energy is the work that is done. So this is the equation we're going to use for power. And we have all the values that we need. Of course, gravity is 9.8. So let's start with the power of hulky. It is 60 kilograms times 9.8 meters per second squared times the height, which is 3 meters. And this is all over 2.2 seconds. When you calculate that, you get 602 watts. the power of bulky is equal to the same mass. He's going up a smaller height. Of course, I have to multiply that by 9.8. And you divide it by his time, which is less, but his height is less. So let's see what power we get for this one. 817 watts. Actually, I don't know where this number came from. This is not, it's 802 watts. Okay, so obviously our more powerful person here is going to be bulky, who had the better strategy of doing less height above bleachers, but in less time. Okay, our next problem is some data analysis. So in this problem, we are going to look at the data for two springs, spring 1 and spring 2. It says, what are the spring constants of each spring? Now, the spring constant of each spring is to figure out what the slope is. So let's try to find the slope of the square slope. First thing you want to notice, it doesn't start at 0, 0. So you can't just do like a simple figure out where it is at 1 and assume that's the rise of a run. What you would want to do in this case is choose 2 points or do rise over run here. If I choose these 2 points, I can do my y2 over, minus y1 over x2 minus x1. That gives me, I'm assuming that's about 4 minus 2 newtons all over 0.2 minus 0 meters. And you end up with 2 over 0.2, which is equal to 10 newtons per meter. For the other one, I am going to choose, I want it to land on something nice. I'm going to choose these 2 points. So this is for the triangle. I end up with 8 minus 0 newtons all over 1 minus 0 meters, and that gives me 8 newtons per meter. So for the next one, it says how much elastic potential energy would be stored if spring 2, that's the blue spring, were stretched from 0 to 0.4. So elastic potential energy, you can do it multiple ways. This one is actually the area under the curve. So from 0 to 0.4, we could take this area right here. The hard part about this is the fact that it's a little bit hard to estimate where it hits the y-axis. I don't know if I'm angling that line down a little bit too much, but if you estimated it as close as you can, your answer should be pretty close to the actual answer, and so I wouldn't mark you down for it. On top of that, on the test, you will have some nice values and some lines on your graph, so you wouldn't have to estimate. You could just follow the line and figure out where it lands on the y-axis. So let's do the area. That's 1/2 area of a triangle, 1/2 base times height. It actually equals out to our elastic potential energy equation of 1/2 force delta x. And that would give me a value of 1/2 base is 0.4, and the height is 2.5. So I would end up with 0.5 joules. Another way to do this is to actually use the other elastic potential energy equation, which is 1/2 K delta X. We're going to use the K for our spring 2, our triangle equation, and this one will give us a more accurate value we're stretching it. This is delta x squared, so be very careful about that. I almost missed that. And I'm stretching it 0.4 meters squared. So when you calculate that value, you get about 0.64 joules. So it looks like I estimated this a little bit too low here because my estimate was 0.5. But like I said, I'm looking for the correct work. If you estimated it, but you still tried to find the area under the curve with a bad estimation, you'll get full credit, and on the test you will have some nice lines so you don't have to estimate it. The next one is how much energy would the spring store if it was stretched from 0.4 to 0.8. Now this one is a good problem. We are stretching it, and this time it's not a nice triangle. It's actually a trapezoid. So what I tell my students is to divide it up. You can have a rectangle and a triangle. Again, we'll have to estimate that and add those two areas together. But what I actually like about this one is that we already have the area of this little guy. And so if we were to find the entire area here of this whole thing and subtract this small area, we could get an accurate area for the spring. So let's see if we can estimate that pretty closely. Here, I'm going to estimate that the area under the curve is, so that's 6.5. So again, these are estimations, and as long as you do the work correctly, you will get points for it. I'm going to do the area of that big triangle. 1/2 base of 0.8 times a height of 6.5. That is for this big red triangle. All right, so I end up getting 2.6 joules. I want to subtract that small triangle, so 0.64 joules, and that gives me 1.96 joules. In the answer key, you'll see 1.92. Like I said, they're pretty close and it's an estimation. So if you get somewhere around here, that would be fine. All right, last problem. We've got a 50-gram dart. Be careful with your units because we don't use grams, and I know a lot of students think that we do, but we actually use kilograms for mass. So here our mass is 0.05 kilograms. I moved it to the left 3 spaces, or divided by 1,000. We have a spring, and the spring is compressed, so that's delta X of 0.05 meters. If 1.25 joules of work were required to compress the spring, what is the spring constant? So work is energy transferred in, 1.25 joules. So you can think of work as energy. And since we're working with a spring, we are going to use our work and equal it to our our elastic potential energy equation. And our unknown also is the spring constant. So we're going to take our work, we're going to set it equal to elastic potential energy, which is 1/2 K delta X squared. So we get 1.25 joules is equal to 1/2 K times 0.05 squared. And I'm going to multiply the 2 to the other side. I end up with 2.5. And then I'm going to divide the 0.05 squared. That cancels that out. And I get 1,000 newtons per meter. All right, what is the maximum velocity of the dart after the spring has transferred its energy to it? So obviously we've got velocity. Velocity is kinetic energy. So all our elastic potential energy here is going to transfer to kinetic. So I'm going to say kinetic energy is 1.25 joules. And we want the velocity, which is equal to 1/2 mv squared. So we can solve for velocity. They gave us our mass, which we didn't need for part A, but now we need it for part B. And we are going to divide half of 0.5, which is 0.25. And we end up getting a value, I'm going to move it down here. Velocity squared is equal to 5. Take the square root of both sides, and you end up with 2.24. Okay, let's do the height. If it were fired vertically, what height would it reach? Again, our energy is going to transfer. So I start off with elastic potential energy of 1.25. It turns into gravitational potential energy. So that's 1.25 joules. The equation for that is mgh. So 1.25 joules is equal to mass of 0.05 times 9.8 times height. If I multiply these two together, I get 0.49. So if I divide that by both sides, I get 1.25 divided by 0.49. Our height ends up being 2.6. Okay, last problem. Dart only reaches a height of 1.5 meters, so this is my height. How much energy was lost to heat? So if energy was conserved, it reached the 2.6 meters, but reality is we've got air resistance, which takes away from the gravitational potential energy, and that converts the energy to heat. So we're going to have less height than we expected. So all we want to do is figure out how much energy was lost, and what you can do is first find out how much gravitational potential energy it would have if it reached the 1.5 height. So that would be 0.05 times 9.8 times 1.5. And that gives me 0.735 joules. And then all you have to do is subtract it from the energy that it started off with, which is going to be the 1.25. So I'm going to subtract this from the 1.25 joules that we originally had, and that gives me 0.515 joules lost. And when we say lost, it isn't actually lost, it is transferred. So I actually really hate that word right there. 0.515 joules transferred. Transferred to heat or transferred out of the system. All right, good luck with this worksheet. Good luck sitting for the test. If you have any questions, contact your teacher.